Okay, let's unpack this. If you're someone whose day, revolves around pork specs, material science, fighting corrosion,
All of it. Understanding fluid dynamics.
yeah, figuring out precisely how much dynamic load a complex machine frame can truly bear, you basically spend your day translating these abstract mathematical principles into rock-solid functional reality.
You're an operative builder. That's really the heart of it.
In every sense of the word, yeah. Whether you're fixing a multi-ton excavator or, optimizing an engine assembly on a high-performance vehicle.
And our mission in this deep dive is, well, it's custom tailored for you. We're going to show that the precise technical principles you apply every single day.
The ones from the engineering handbooks and shop manuals.
Exactly. Those principles are rooted in something far older and, frankly, profoundly philosophical.
So our sources today are a bit of an unusual blend.
A very unusual blend. We've got the incredibly precise language of modern mechanics statics, rigid body dynamics, thermal stress analysis.
And we're mingling that with the core foundational philosophical texts of speculative Freemasonry.
We're looking for the common root, the universal truth that, ties the integrity of a machine to the integrity of a man.
To find the intention behind that concept of the grand architect in every successful piece of work you handle.
Yeah, and the core thesis we're exploring, it's not just theory, it's a living blueprint. The calculated concepts and the precise tools you use to build things that are stable and lasting on Earth.
Your technical expertise.
That expertise is precisely the same principle used symbolically to build character, to build a life that lasts.
So when you realize that the technical skill it takes to turn a wrench the right way or analyze a complex stress point in a chassis is an echo of this ancient discipline.
Then your trade isn't just about technical labor.
No, it's rooted in the profound application of geometric and, dare we say, divine law. This deep dive shows you, the expert technician, that your practical skill is itself a pathway to a deeper understanding.
Let's get into it.
To begin, let's set the scene with the foundations of stability and structure. I mean, that's where every build or repair has to start.
Absolutely.
We're looking at foundational engineering mechanics, the realm of statics, rigid body basics, trusses, internal forces. Every component you fabricate or deal with has to handle load without failure.
That's right. And engineering quantifies this stability with incredible precision. A key concept here, especially when you're dealing with beams and frames, is that relationship between stability and geometry.
Okay.
Specifically, we have to understand the moment of inertia, which is often denoted as I.
And the related concept, the section modulus, S.
Right. And for our listeners who deal with this stuff daily, it's probably worth reviewing why these numbers matter so much.
Definitely.
They're critical because they show that a beam's resistance to bending or deflection isn't just about the material's modulus of elasticity. It's overwhelmingly about the shape.
The distribution of that material.
The distribution of that material relative to the axis of bending. The moment of inertia calculation, fundamentally, it involves taking the area of the cross-section and multiplying it by the square of the distance from the neutral axis.
And the distance squared part is the kicker, right?
Precisely. Because that distance is squared r squared, moving material further away from the center axis, that neutral axis, it dramatically increases the beam's stiffness and its resistance to bending.
Which is why structural engineers, or a mechanic, building a frame, will rely on shapes like I-beams.
Or T-sections or U-sections, yeah. Not a solid square bar, even if the total cross-sectional area of material is the same. An I-beam puts most of its material, the flanges, as far as possible from the center.
Maximizing IM. It's the ultimate lesson in efficiency.
It is.
You're distributing strength exactly where the stress is highest. You see it everywhere, from the frame rails of a semi-truck to the wings of an airplane. The geometry dictates the performance.
It really does.
And the section modulus, that takes this a step further, doesn't it?
Yes. S is calculated by dividing the moment of inertia, I, by the distance from the neutral axis to the outermost fiber, C. So if I told you about the beam's stiffness...
It's resistance to deflection.
Right. Then S tells you about the maximum stress the beam can handle before it yields, before it permanently deforms.
So if you're designing a high-speed rail car or a skyscraper, you need an extremely high moment of inertia.
To ensure rigidity and to minimize deflection, even under dynamic loading and shear forces. This calculation is the physical embodiment of, well, wisdom, the intelligent design needed to foresee the loads and calculate the necessary form.
We see this principle even in the simplest, most ancient machines.
Mm.
Our sources reference the inclined plane.
Of course.
If you ever had to move a massively heavy component up onto a flatbed, you intuitively understand this.
Absolutely. The physics of it involves calculating the tension P needed in the cable, the perpendicular pressure Q on the plane, and the angle alpha of the incline.
It's a fundamental exercise in resolving forces into their components.
Horizontal, vertical, perpendicular to the surface. By resolving the load and the gravity vector, you calculate the minimal force needed to overcome the load and friction. You're maximizing efficiency through geometry.
And then there's the lever, the ultimate symbol of mechanical advantage. A small force F can balance a much larger weight W.
If the distances are arranged correctly, yeah. It has to obey the law of moments.
F times L equals W times L.
And that mechanical balance of opposing forces is the essence of stability and equilibrium.
So if you have a weight, say 30 kilograms, place 0.4 meters in the fulcrum.
And you apply a force F at 1.2 meters away, the balancing force is the equivalent of a 10-kilogram mass.
That perfect equilibrium, that balance, means the system is stable, motionless.
The structure has to be free of unbalanced forces that could induce destructive moments.
Okay, here's where it gets really interesting and where we bridge that gap, that purely physical analysis, the perfect balance, the quantifiable distribution of stress using moment of inertia. That's all physical reality. How does that demand for perfect equilibrium translate to the moral realm? We've talked about the architecture of steel, but, what about the architecture of a durable, stable character?
And this is the transition. We move from the practical foundations of a physical building to the symbolic foundations of a spiritual edifice.
Right.
In Masonic philosophy, the most fundamental structural symbol is the use of the 3 grand columns or pillars.
Wisdom, strength, and beauty.
Wisdom, strength, and beauty, which is often referred to as harmony. These 3 pillars are said to be the principles that support the lodge.
Which itself symbolizes the universe.
Exactly. And without all 3, the structure fails.
I really appreciate how you link the calculated distribution of stress to moral architecture. Let's break down that map directly.
Okay, so wisdom. Wisdom relates directly to the architectural design and calculation. It's the foresight, the planning phase.
It's mastering the geometry and math to determine the moment of inertia, the shear forces.
All of it. The material properties before a single piece of steel is even cut. It's the intelligence required to foresee the loads that will be placed on the system and to design a structure capable of withstanding them without, over-engineering it.
It's the principle of proper design.
It is.
And from a technician's perspective, applying that wisdom means you are strictly adhering to the design specs. You're not using guesswork or that looks about right.
You are respecting the original calculation.
Exactly. Then comes strength.
Strength.
Strength is the material integrity. It's the physical ability of the structure or the person to actually bear the load that wisdom foresaw.
This requires solid, uncorrupted materials, proper fabrication techniques.
Quality control. If the engineer correctly calculates that the beam needs to be high-yield steel, that's wisdom, but the builder substitutes substandard rebar or an incorrect alloy.
That's a failure in strength.
And the whole edifice is compromised, regardless of how good the original design was. So, wisdom is the mind, strength is the body and material, and both have to be perfectly sound. This makes me wonder, though. In the shop, strength often means over-engineering to save on design time. Does the philosophy permit over-strength? Or does the calculation have to be perfectly precise?
That is a really thoughtful question. The philosophy, especially with its focus on geometry and divine law, it seeks harmony, not brute force. Overstrength, while it might be functional,
It's inefficient.
it often represents an inefficiency, a lack of beauty.
Which brings us right to the third pillar, beauty or harmony.
This is the visible and functional result. It's the intended product of correctly applying both wisdom and strength if the load is calculated correctly
Wisdom,
and the materials are solid.
strength.
The resulting structure stands in beautiful, functional harmony. It's the perfect machine running exactly as designed, efficiently, safely, and elegantly.
And when a bridge collapses, that failure is a manifestation of an ugly, jarring disharmony.
And you can trace it back to a specific failure in either the initial calculation, wisdom, or the material implementation, strength. The physical laws of statics are, they're unforgiving. They demand a kind of moral precision.
That sets a powerful foundation. Now let's drill down into the deep microscopic details of precision. Let's start with one of the most fundamental, yet, I think, misunderstood aspects of machinery.
Mm.
Fasteners.
Oh, definitely.
Every technician relies on a bolt and a threaded hole every day, and yet the underlying physics are surprisingly non-intuitive.
Indeed. The standard assumption that when you torque down a bolt, the load is uniformly distributed across all the threads, that's just fundamentally incorrect. Design analysis reveals a shocking level of stress concentration.
Our sources confirm this critical insight that 6 threads at most carry the significant portion of the load.
At most. And this phenomenon is due to the cumulative effect of elasticity and these minute pitch errors between the mating threads of the bolt and the nut material.
Let's explain the mechanism for our audience. I think the techs out there would appreciate the detail.
Okay, so when a bolt is tightened, two things happen. The bolt stretches, it elongates, and the material around the tapped hole, the nut, it compresses.
Right.
Because the stretching occurs before the load reaches the further threads, the first thread, the one closest to the load-bearing face, is forced to carry the vast majority of the load.
As the bolt stretches, it effectively misaligns the pitch slightly with the other threads.
Exactly, which causes the load to drop off dramatically on the subsequent threads.
That's a stunning example of how critical the micro-precision of that immediate connection point is. It means thread engagement depth beyond, say, 6 or 7 threads is often structural overkill.
It really is. It serves mainly as a safety factor or to ensure the material integrity against thread stripping, but it doesn't significantly add to the actual tensile capacity of the joint itself.
And this leads directly to optimal assembly practice, especially around torque specs.
It does. We have to avoid tightening a bolt beyond its yield strength. That's the threshold where it permanently deforms, known as the proof load. But we have to get it close enough.
Because achieving sufficient stretch in that bolt is what provides the crucial clamping force.
Yes. The bolt acts as a powerful, measured spring holding that joint tight against external forces and vibration.
This is why so many modern critical applications use torque to yield, or TTY bolts. You're intentionally torquing the fastener into its plastic deformation zone.
To get maximum consistent clamping force, sometimes it even replaces the function of a lock washer. But that TTY method, it demands absolute fidelity to the specifications, doesn't it?
It demands the highest level of material integrity and measurement precision. It's like a moral absolute.
It is. If you're working with low-grade bolts, old corroded threads, or weaker material, what you might call crappy metal or furniture,
Right.
you simply cannot tighten it to achieve that essential calculated stretch. The material will strip or fail.
So in those specific lower integrity applications where the material can't act as its own spring,
You must rely on an external force, like a lock washer or a thread locker, to prevent vibrational loosening. The mechanical integrity has to be provided by one source or the other.
this necessity for precision and integrity in the physical world, it just perfectly parallels the moral precision required for self-improvement and reliability. Let's look at the tools.
Let's start with the gavel.
Okay.
Operative masons use it to break off the rough corners and, the superfluities of a rough stone to fit it for the builder's use.
And speculative masons, focused on character, use the gavel symbolically.
To divest the heart and mind of vices and superfluities.
So it's about necessary and controlled refinement. Like a technician using a grinder or a file. You're removing material, but you're doing it with a controlled hand to achieve a perfect fit, not just smashing things apart.
Exactly. The goal is a continuous, measured process of refinement, making the mind a living and lively stone, ready for the spiritual temple.
You're removing everything that doesn't belong, all the unnecessary mass, all the rough edges.
So the individual can bear its required load with stability and integrity.
And then there's the square, the tool for achieving that precise alignment. The idea of living upon the square is ancient, far older than the modern craft.
Oh, much older. It's cited in the ancient Chinese text, The Great Learning, which dates to the 5th century BC.
And that taught the golden rule, right?
That men should abstain from doing unto others what they should do to them. The text explicitly called it the principle of acting on the square.
It demands perfect reciprocal moral alignment. Your actions are measured equally against the measure you apply to others.
That's it. If your bolt torque requires 50 foot-pounds on one side of a flange, moral squaring requires 50 foot-pounds of honesty and fairness in all your dealings.
So what about vertical alignment? That's the plumb line.
Vertical integrity is checked with the plumb line. This symbol ensures the structure is perfectly vertical, standing upright against gravity and lateral loads.
And there's a reference to this in Scripture.
Yeah, in the book of Amos, where the Lord sets a plumb line in the midst of Israel. Morally, it guides integrity and truth. ensuring your actions, your intentions, and your diagnosis are all aligned, upright, and consistent.
A technician can't perform an accurate measurement if their reference plane or their instrument is out of plumb.
And similarly, the internal self has to be calibrated and aligned with truth before any external action can be reliable.
That integrity is also about daily workmanship, which brings us back to the mechanical side. The concepts of tolerance and surface quality. Technicians wrestle with this constantly.
You might have 1,000th of an inch to play with, and that margin is absolutely critical.
So we deal with three standard types of fits.
Right. Based on the relationship between the maximum and minimum sizes of the mating parts, we have clearance fit,
Where there's always clearance for free movement.
interference fit, where there's always interference. You need force or thermal expansion to mate the parts, like a press fit,
And transition fit.
which can be either a clearance or an interference, just depending on where the parts fall within their specified tolerances.
For our highly technical audience, the choice of fit is a critical design decision. It's tied to the function rotational speed, heat transfer needs, load bearing. For example, why would a tech need to be absolutely certain of a measurement before attempting an interference fit?
Because if you miscalculate the tolerance for an interference fit, especially one relying on thermal expansion, say, heating a ring gear to shrink it onto a shaft, you risk catastrophic material failure.
Or seizing the components permanently?
Exactly. The high thermal or physical stress involved requires absolute certainty and measurement truth. This technical necessity forces the practitioner to exercise caution and integrity in measurement.
And that necessity for caution extends to the final defining characteristics of the material itself, surface texture.
Yes, surface texture defines the repetitive or random deviations, the roughness, waviness, lay, and flaws that deviate from that nominal perfect surface.
The performance of a high-load bearing, the seal integrity of a gasket.
The friction characteristics of a clutch plate, all of it hinges entirely on controlling these micro deviations. If you can't trust the surface, you can't trust the fit, and you can't trust the seal.
This mechanical necessity for flawless integrity and caution finds its perfect moral mirror in the required conduct of a Mason, particularly the newest members.
Absolutely. Here we introduce the 3 precious jewels of an apprentice: a listening ear, a silent tongue, and a faithful heart.
These ensure the internal and external integrity of the individual.
They do. For a mechanic, the listening ear is vital for diagnosing a machine. You listen to the subtle shifts in engine noise or fluid sound before you act. But philosophically, it is for instruction and for the needs of others.
And the silent tongue. In a shop environment, a silent tongue prevents costly errors caused by distraction or speculation.
Precisely. The silent tongue is for maintaining peace in the lodge, but more importantly, it teaches the restraint required to keep silent before the organization's critics.
To ensure the craft isn't brought into disrepute by imprudence or loose talk.
It's the caution required to analyze a situation fully before you render judgment or speak ill.
This focus on defense of the integrity of the whole is key, especially when you're newly entrusted with complex information.
Whether it's the mechanics of a new diesel engine or the traditions of a fraternity, it is so vital that the newly initiated Mason is also presented with a new name, which is caution.
Caution.
It teaches the individual, who is still barely instructed in the rudiments, to be cautious over their words and actions, especially before critics of the organization. Just as a technician must be cautious not to exceed the proof load on a critical bolt.
They have to be cautious not to exceed the capacity of their character or the trust placed in them.
Mechanical precision demands moral caution.
Okay, switching gears now. Let's move from statics and the precision of structure to the movement and controlled flow of energy.
Dynamics.
This is the realm of dynamics, areas critical to any equipment technician dealing with hydraulics, pneumatics, and thermal management.
We can start with a principle that underlies massive mechanical power multiplication: Pascal's principle in hydraulics.
One of the most beautiful and contained forms of energy transfer.
It is. The principle states that pressure applied to an enclosed, incompressible fluid is transmitted undiminished throughout that fluid.
And the genius of it is that pressure, P, is constant, but the force, F, is multiplied by the ratio of the areas.
Exactly. Since P1 equals F1 over A1 and P2 equals F2 over A2, if you apply a small force on a small input area,
that pressure is transmitted equally to a large output area to generate a huge force.
Right. And the resulting force, F2, is multiplied directly by the ratio of the areas, A2 over A1.
This is what allows a small pump and a person's light touch to lift an entire semi-trailer or articulate massive booms. It's controlled constructive power.
The direction of energy for maximum purposeful effect.
It's important to stress, though, that while force is multiplied, energy is conserved. The small input force has to move a much larger distance than the large output force.
That conservation of energy is the mathematical truth of the system. The power is contained and focused. And this concept, it immediately relates to one of the constant battlegrounds for technicians: cooling system design and fluid integrity.
Oh, absolutely. Our sources dive into the complex issues that arise from seemingly small design flaws in thermal management.
Like the example of the Vortec engine heads.
Yes, a poorly designed fitting on the manifold allowed air to be sucked in when the engine cooled off, creating these tiny air pockets in the system.
And that small design flaw, a failure of containment and flow control, led to multiple catastrophic consequences.
First, the air pockets caused the oxidation inhibitors in the red antifreeze to get depleted.
Which turned the fluid highly acidic. And second, the constant cycling of air pockets under pressure led to thermal stress concentration.
Resulting in hairline cracks, usually between the middle cylinders and the heads, causing coolant loss and eventual engine failure.
It just shows how a flaw in flow management can corrupt the very fluid that's meant to protect the structure. It leads to a total breakdown of integrity.
There's also the counterintuitive physics of airspeed that challenges a mechanic's assumptions. It's so tempting to think that faster airflow equals better cooling.
And our sources suggest that's often incorrect, especially at high velocities.
Right.
At high speeds, aerodynamic friction and localized adiabatic compression cause temperature spikes. The red-hot space shuttle example illustrates this perfectly. Friction and rapid compression generate immense heat, which overwhelms the cooling effect of the airspeed itself.
And speed-induced shear and turbulence, a loss of smooth laminar flow that causes a massive loss of heat transfer capacity.
Yeah, because the fluid, whether it's air or liquid, can't efficiently contact the hot surface.
And yet, we know that flow has to be regulated. The observation is made that while manufacturing engineers are under intense pressure to cut costs,
The thermostat remains.
it remains a simple, necessary, and universally used component for system performance.
The thermostat is the ultimate regulator of flow. It doesn't just maximize speed, it manages temperature. It restricts flow when the engine is cold and opens it precisely when the system needs to shed heat.
It prevents thermal shock.
And ensures the system operates in its optimal temperature window, which maximizes efficiency and minimizes stress. It's the perfect mechanical illustration of temperance.
Now let's connect this. This contained mechanical and thermal energy, Pascal's force, the regulated flow, the managed heat to spiritual power. For the fellow craft, the key is the mastery of emotion.
This mastery is essential because it places the dynamo of living power, which is sometimes described in philosophical sources as the seething energies of Lucifer, or cosmos power, at their disposal.
This energy is the creative force, the raw potential of the universe.
It is. And the key lesson here is that this power, like hydraulic pressure or immense thermal energy, it must be used constructively and selflessly. Uncontrolled, these energies are absolutely destructive to the self and to the community.
That concept of channeling destructive potential into productive force introduces the degree of transmutation.
The constant ethical transformation required of the individual, the lesson is profound. The hands that slew must learn to lift the fallen. The heart that hates must learn compassion.
And this mirrors a critical, often painful process in metallurgy, tempering heat-treated steel.
It does, as quenched steels are incredibly hard, but they're brittle and filled with internal residual stresses.
Like someone who is rigidly strong but emotionally brittle.
Precisely. Tempering involves reheating the steel to a precise lower temperature to impart plasticity or toughness by relieving those residual stresses from the quenching process.
It changes the crystal structure.
It imparts necessary toughness and resilience, but, and this is key, it's inevitably accompanied by a measurable loss in superficial hardness and strength.
There's a necessary trade-off.
You lose the brittle, rigid strength for essential, enduring toughness and resilience. The willingness to submit to that tempering process is the moral equivalent of the fellow craft's transmutation.
And we find this idea of contained, fundamental, transformed energy reflected in the Hermetic tradition as well.
Yes, the Emerald Tablet of Hermes. The hidden knowledge it speaks of, Kiram Kalat Mekasad, or one in essence but three in aspect, refers to the universal seed or secret fire that creates and sustains the world.
So this fire, this fundamental energy, it must be managed and understood.
Right. The tablet states the father is the sun, the mother is the moon, and the wind carries it, linking universal cosmic energy to the physical world, which is sustained by this same essential but volatile force.
So the ability of the Mason to handle this inner power mirrors the mechanic's ability to precisely regulate pressure, flow, and heat within a complex machine.
That's the parallel.
So what does this all mean when we bring the discussion full circle to the supreme importance of design and geometry?
I mean, we've covered statics, dynamics, material precision. Every machine, every structure, from the micro-tolerances of a fitting to the enormous forces in a hydraulic system, is a direct result of applied geometry.
Geometry isn't just a branch of math, then.
It's the universal language of creation. In the Fellow Crashed lecture, it's described as the fifth science, by which we curiously trace nature through her various windings to her most concealed recesses.
And it's through the immutable truths of geometry that we discover the power, the wisdom, and the goodness of the grand artificer.
The designer of the entire vast, elegant machine of the universe.
And this tradition of seeing working tools as moral or sacred symbols is ancient. This idea wasn't invented yesterday.
Not at all. We find evidence in the Book of History, one of China's earliest classical texts, dating from the 20th century BC. Officers are instructed to apply the compasses.
So the tools of the builder were always linked to the governance and morality of society.
Always. And there's that powerful, almost mythical connection stemming from the flood story, the transfer of science.
The two pillars.
The tradition says that knowledge was inscribed on two pillars, one of marble to resist fire, and one of brick, or lators, to resist water, to transfer scientific and geometric knowledge across that great catastrophe.
And one was found by Hermes, carrying the celestial wisdom.
And the other by Pythagoras, who famously went on to teach geometry using numbers as spiritual emblems.
But only after enduring 20 years of rigorous testing in the Egyptian mysteries to learn the hidden wisdom.
It shows that geometry is the universal, immutable language of creation, proven capable of surviving even cataclysm.
And the ultimate symbolic dimension is embodied in the triangle, not just any triangle, but the right-angled triangle, which every tech knows from the Pythagorean theorem.
A squared plus b squared equals c squared.
Right.
In symbolic language, particularly the famous 3-4-5 triangle, we see the perfect union of the spiritual and the material.
So the base, measured by the number 3, the sacred number of the triangle,
represents the deity and the divine, the immutable plan, the source of wisdom.
and the perpendicular, measured by 4, the number of the square, represents the earth, the material, and the human.
The realm of strength and application.
And the hypotenuse, measured by 5, represents the resulting nature, the soul and the body, the unified, perfected state.
Because 3 squared, 9, plus 4 squared, 16, equals 25.
And the square root of 25 is 5. It's the perfect, harmonious result of the union between the divine plan and the disciplined, material application of human effort.
The hypotenuse is the line of connection that unifies the sacred and the profane.
And this geometry is so fundamental that the letter G in the fellow craft degree denotes both deity and geometry.
Recognizing that geometry is the only reliable science connecting the physical creation with the divine plan. Geometry is the map we use to find the grand architect.
This powerful symbolic framework leads us directly to the legacy of the operative masons, the actual builders who carried these tools and established these secrets.
And these groups were not just local laborers. Earliest known architects groups like the Dionysiac artificers in the Mediterranean world and the Commacene masters in Lombardy were secret, oath-bound fraternities.
The Dionysiacs, for instance, were a great corporation who often monopolized the building of temples and stadia.
They possessed secrets of geometry and construction that gave them a clear competitive advantage.
And this tradition carried through to the Middle Ages, where the name Freemasons distinguished the cathedral builders.
Who often traveled across Europe under a universal order, carrying their own secrets of design and materials.
And that set them apart from the local guild masons, whose operations were geographically restricted.
The Freemasons represented a higher, more widely dispersed order. They carried secrets of design and construction that were fiercely protected, often under severe penalties for revealing them. Their work demanded the highest standards.
Wisdom, strength, and beauty.
Which enabled them to construct the great cathedrals that still stand today, structures that defy simple analysis of the period's technology.
And we see that bridge between the practical operative skill and the philosophical speculative thought really solidified during the Enlightenment.
With figures like Sir Christopher Wren.
The King's architect who designed the Sheldonian Theatre and rebuilt 52 churches in London after the Great Fire. He embodied this blend.
And even more influential was Dr. J.T. Desaguliers, a brilliant natural philosopher, mathematician, and an expert in geometry and optics.
He was a key figure in the early 18th century.
He took the established operative structure and formalized the speculative, philosophical aspects, emphasizing the moral lessons inherent in the builder's tools. He helped transition the craft from focusing on physical stone
to focusing on the living and lively stone of self-improvement.
It's also worth noting that even before the formal creation of the Grand Lodges and that full philosophical shift, Masons were already classified into 3 distinct titles:
Apprentice, Fellowcraft, and Master.
Yes. This structure existed when the craft was still largely an operative endeavor, which shows that the hierarchy of skill, knowledge, and moral responsibility was formalized long before the philosophical revolution took place.
So the progression from apprentice, learning to listen and obey, to Fellowcraft, mastering geometry and energy, to Master,
the architect and philosopher.
It perfectly mirrors the stages of technical mastery.
So to synthesize the dual nature of this deep dive, the pursuit of mechanical perfection accuracy and tightening a bolt just below its yield strength, calculating moment of inertia for stability, ensuring fluid dynamics are pure to avoid corrosion.
In applying Pascal's principle for multiplied controlled power.
All of it is a practical, daily manifestation of that ancient moral pursuit of integrity, caution, and spiritual stability.
So the technical work itself, when it's executed with precision and fidelity, is a constant, tangible lesson in moral law. Your hands are literally engaged in the physical translation of geometry and force.
And that act, when performed with diligence, transcends mere labor.
A Mason's great business with life, as one source beautifully puts it, is not just to fix the immediate problem.
It is to read the book of its teaching, to find that life is not the doing of drudgeries, but the hearing of oracles. Your daily work is the oracle, if you listen to the materials and the immutable laws governing them.
We talked about the 3 degrees: apprentice, fellowcraft, and master. And the source material notes that the degree of Master Mason is veiled.
Concealed by a blue veil that divides the seen from the unseen, the mortal from the spiritual.
And this hidden path is fixed forever on the 7 stars above the top rung of the ladder.
Which is a deliberate parallel to the ladder of 7 steps found in the ancient Mithraic mysteries, symbolizing the ascent through the planetary spheres toward liberation.
So next time you pick up a torque wrench or calculate stress concentration in a high-load assembly, consider this.
The laws of physics and geometry you obey, moment of inertia, elastic limits, the conservation of energy, are symbolically those very stars. They are guiding the way toward perfecting yourself, moving beyond the brute force of the material world and to the harmony of the grand architect's design.
It's not just a blueprint for a machine. It's the blueprint for a life well built.